it cut off the recording. Yeah. I guess we got a sticker. I don't see a sticker pointer. Well, that's. So we are fortunate to have a special seminar tonight. Let you go see the by Nishant Gupta visiting us from NISER, long way away, Bhubaneshwar. And he will tell us about Worldsheet CFT, Celestial CFT, and AdS3 CFT perspective. And you are around. I thought. Yeah. Yeah. You know. Okay. Hello everyone. Thank you all for coming. It's Euclidean and I would like to thank TV. Right. So I'm going to talk about the recent work that I did with Shamit Banerjee and Satvik Mishra, both at NISER Bhubaneshwar, which is based on this archive number, and where we look at the connection between Worldsheet CFT2 and Celestial CFT and sort of give an AdS3 CFT perspective on the whole thing. And along the way, there will be a lot of things that we would want to look at. Can you see the person? Yes. It's not maybe you probably use Java. Oh yeah. Oh no. Okay, so actually I'll have to use my hand to point. Okay, so all right. Okay, it's fine. Okay, before going into the specifics of my talk, I would just like to introduce you to the topic a little bit, give a general overview of what celestial holography is, and this will be very, very general slides without any hopefully technical stuff. Right. So okay. So celestial conformal field theory has become one of the leading candidates for flat space holography, and if you go by the logic of holography in the usual AdS-CFT case, so this states that a quantum gravity is two-dimensional asymptotically flat space-time is dual to a celestial conformal field theory, which is present on d-dimensional sphere at the boundary null infinity. So your boundary null infinity is d plus one dimensional, and at the end of it there is a sphere which is d-dimensional sphere, and so your celestial CFT lives on this sphere. The name celestial CFT comes because this we consider as a celestial sphere, and so hence theory is defined as celestial CFT. Right. So it is an example of 4-dimension 2 holography. And it's a very different from this conventional 4-dimension 1 holography that we are used to in the form of AdS-CFT correspondence, where the dual theory to quantum gravity lies at the 4-dimension 1 boundary of the space-time. But here, like I said, this dual theory lives on the d-dimensional sphere at the boundary null infinity. Okay, so the global symmetry group of this celestial conformal field theory is Poincaré group, which is ISO d plus 1, 1. There is no surprise because same group is also the isometry group of d plus 2-dimensional flat space pairs. So from the holography, we know that the dual theory and the bulk theory should have both same symmetries. So therefore, this Poincaré group is the symmetry group of CFT2.
Is it known what a celestial CFT is?
So this is mostly like bottoms-up approach. There are now, so recently there have been a lot of these top-down approaches where people have understood like what might be the string theory that can correspond to social conformal theory. So yeah, there is some understanding now, but usually it started as the bottoms-up approach, but nowadays we have one. Right. So now this Poincaré group, as we all know, is like the semi-direct product of Lorentz group and translations. So the Lorentz group S3 plus 1 comma 1, subgroup of this group, acts as a conformal transformations on this d-dimensional sphere, whereas the translations, they are realized as the internal symmetry. And by internal symmetry, I mean that, let's say, if you have a conformal dimension of some primary, these translations can act as the weight shifting operators. So they will shift the weight of the symmetry. So it's not a space-time symmetry from the point of view of three-dimensional theory, but it's like some additional symmetry. Right. Okay. And monographically, we expect that this correlation functions of Celestial CFT, three-dimensional Celestial CFT, compute the scattering amplitudes of t plus two-dimensional aspects. Right? That's like the basic prerequisite for it to be a monographic theory. So, okay. So now I want to say that this celestial conformal field theory is very different from your conventional conformal field theory. First of all, the symmetries are different, right? And then the second thing is that in the celestial conformal field theory, the lower point correlation functions like 2-point functions, 3-point functions, they are distributional in nature. That means there is a direct delta term associated with the spatial dimensions, which is unlike in the conventional CFT, you have a power law. Here you have this distributional nature, and this is an artifact of the like momentum conservation in the scattering amplitude. So if you want your scattering amplitudes to be momentum conserving, what it does is that it makes the celestial CFT correlation functions distributional in nature. Right. So, and another difference is that the primaries and descendants, they are defined with respect to SL2C group, which is like a conformal group. So the boost operators define the primaries and descendants of the celestial conformal field theory, which is like in conventional CFT where you have dilatation operators and spatial conformal transformation that does this.
Also, is the global symmetry group just Lorentz, or is it BMS?
Right. So the global symmetry group will be for Poincaré. I'm not talking about BMS yet. So let's be finite for now. And so it is the full Poincaré group. But the primaries and descendants, they are defined with respect to the Lorentz group, which is the subgroup of Poincaré. Right.
So
yeah.
In ordinary CFT, primary descendant point. As it is.
No, but let's say if you have a three-dimensional CFT, right? So you have a right. So let's say you have a if you have a three-dimensional CFT, so you have a Lorentz group, and then you have these dilatations and spatial conformal transformations, right?
Three-dimensional CFT.
Right, but so this conformal group is like extra generators of this Poincaré group, right? So yeah, I mean in two-dimensional CFT. So basically this dilatation operator in this d-dimensional so here what I meant is that the Lorentz group has these boost eigen states, right? These boost operators. So the representations are defined with respect to these boost operators. So that's what I meant when I said that they are defined with respect to SL2C. So it's the Lorentz operators in, let's say, two dimension if I am. So these Lorentz in the usual case, you will have this dilatations and spatial conformal transformation that acts that are apart from this Lorentz transformation that their primaries and descendants are defined. But here it's just the boost operator.
The boost operator acts as
No, but like in two dimension, if you have let's say SL2C, right, and then you have this X. Okay, right. Just a second, I'll just come back.
Okay.
So, right. So, okay. So, what I said was the celestial CFT. It's the symmetry group is Poincaré group, but there are a lot of problems associated with this. Primarily, that there's a distributional nature of these correlation functions. promoting or like bring in the technology of this AdS-CFT, non-conventional CFT, what people have started considering are these Celestial CFT with only Lorentz invariance, and they were first introduced in the work of Mendel, Sharma, and Strominger. Right. So in this this Celestial consumer field theory, these correlation functions have the standard CFT form, and there are specific algorithms which exist, following which one can reconstruct the Poincaré invariant S matrix elements from the Celestial CFT correlation function. So basically, these what you can do is, if you have a flat space-time and if you this slicing of the flat space-time using Lorentzian AdS3 or Euclidean AdS3, so the calculation of this Witten diagrams that is at the boundary of this slicing will correspond to these amplitudes which are just have Lorentz invariance, and there are no Poincaré invariance. And the way you do and the way you reconstruct them is that you integrate over the whole slices in the flat space-time to get this Poincaré invariant S matrix elements form. Right. So now this examples of these theory include Liouville theory, which is coupled to some conformal vector fields. So there have been like bunch of these works where people have considered Liouville theory coupled to some, let's say, -3/2 fields or Cauchy algebra, and they have constructed examples of these theories, which then calculate these symmetric vector scattering amplitudes in flat space-time. So just from the CFT with only Lorentz invariance, you are able to construct these scattering amplitudes of the flat space-time. So you don't need Poincaré invariance. Only just consider Celestial CFT Lorentz invariance.
It's something philosophically confusing about this, at least in the context of truth. So you can come back like many different ways in formation, and you'll get presumably many different Celestial CFT magnitudes. But I think it's a point I think Sam has been making correctly, at least one. There should have been one holographic theory that accessed all of these backgrounds at once.
Right.
Because you could build many little black holes. Use arbitrarily big region. Is that meant to be captured by this?
No, I think these are constituents of that theory, but it's not a complete theory because it doesn't have the required symmetry. So these can be like some sort of sector in those theories, but it's not like a complete theory.
So this is meant to capture some aspects of
Yeah, it's very
asymptotic flat space, four-dimensional asymptotic flat space. What aspect? I mean,
no. So basically, what this work has shown is that, like, let's say if you have an AdS3 diagonal scattering amplitude, what you can do is from these Lorentz invariant, just the Lorentz invariant Celestial CFT operators which have these power law, you can recombine them and then show that they will calculate symmetry diagonal scattering amplitude. So there's an algorithm yet that you recombine them in a specific way, because what you can do is you can decompose that conjecture in the spatial dimension as some, like some sort of a pole behavior, and then if you like recombine them, you will be able to reconstruct the symmetry diagonal scattering.
that's somehow just like tree level scattering.
Yeah, that would be. So everything here, like for now.
So quantum theory should be able to capture the exact answer. It's conceptual.
Yeah, but the program so far is so that we have only been able to like, because it's if you have a complete string theory, that will like complete Celestial conformal field theory, that is toward to some string theory, then it might be able to calculate the full sort of all loops and everything. But so far, because of this approach, because it's a bottom-up approach, we don't have any string theory example of it. This basically just capture this tree-level scattering amplitudes, and then once you consider loop level, you'll have some quantum correction. Then you have this. Basically, this idea is just for tree level.
I've heard this claim before that in Celestial CFT lower endpoint functions are distribution. I'm confused what that means because I would say that generically the endpoint functions of quantum field theory are distributional. So are you saying that it's more singular than the usual quantum field?
No, so because when we go from this momentum space scattering amplitude, so these when we are looking at a particle, in the scattering of the particle, these particles essentially sort of one point at the celestial sphere, right? And I think it has more to do with the fact that these are momentum space scattering amplitude, the way comes about in the celestial distance, that there is a distributional nature to it. So basically, it just fixes the direction to which the particle can reach in the celestial sphere. So it's sort of that catching that property.
So it's a delta function.
Yeah, it's a delta function. Right? That's what I meant.
Severe. Okay.
Yeah. So when I say distributional nature, I mean delta functions with that. Right. So now, so if you want to, one approach to develop flat space sonography is maybe take a limit of AdS-CFT and see what it gives. And there have been various programs where people have tried to take the limit of AdS-CFT and see if it gives you any, valid things for the flat space holography. So what my talk is going to be about is that I will talk about how a subset of this class of Celestial CFT can arise from AdS3 CFT correspondence. And I will be only focusing on SO1, 3 invariance because my string theory has only SO1, 3 invariance in the target space, right? So, but the technology can also extend to any theory with Poincaré invariance, right? Sorry, not Poincaré invariance, but SO2, 3 invariance, a full conformal group of Euclidean entities CFT. So I will start by mentioning with that, and then I will just go to SO1, 3 invariance only. Right. So this is the sort of a diagram which says that if your square is like the set of all the Celestial CFT2, the circle with the gray color, it sort of represents all the Celestial CFT2, which is toward to some near boundary limit of string theories on AdS3, which is I'm going to explain this terminology in a second, like what it means by near boundary limit. So we will just capture the subset of the full set of Celestial CFTs.
The Celestial CFT have this rule.
Sorry,
Restricted to the subset of celestial two-dimensional CFT that have AdS3 rule.
No, so this is near boundary. Also, we will see that instead of AdS3, you are going towards the near boundary. So these are like long strings which are sort of stay near the boundary of AdS3. So those are the ones that is explained by these Celestial CFT, not like the full AdS3. Like not fully. It's like a specific sector of long strings. Right. So the outline of my talk is as follows. That first I will explain what it means by when you go towards the boundary of Euclidean AdS3. And then I will talk about my proposal that we are trying to give through this work. And then we will look at what it means, like what it means to have the near boundary limit of CFT2 point function and how various structure arises from that limit. And then I will talk about like a bunch of all these theories that Lorentz invariance and how their near boundary limit looks like. So this will have some massive field theory, near boundary limit of string theory, and Einstein's radial, and then I will conclude the talk. Right. So first, let's start with this concept of zooming near the boundary of Euclidean entities, what it means. So suppose I consider conformal field theory on Euclidean entities background, and now this background is given by this particular line element. There is a conformal factor 1 by eta square in the denominator, and that means that the boundary is at eta equals to 0. Now, the conformal Kelly vector fields of such a background can be easily found by solving this box equation, and once you solve it, you find that there are 10 parameters of the now the CKVs can be written in the following form. You can write curly LM. You you can write this curly LM, curly L bar M, and curly PRS. Right. So as you can see, M runs from three values, 0, plus, minus 1, and R and S runs from plus, minus half. So that together gives you 10 constant equilibrium. Now, let's say I try to find the commutators of these vector fields. What I will see that these vector fields obey SO4, 1 algebra, which is like the conformal algebra of Euclidean AdS 3. Right. So you can see that this curly LM and curly L bar L, they form this two copy of so together they form this SL2C algebra, which is like a conformal group SO1, 3, and PRS transforms like a vector under these curly LMs and L bar Ms, and their commutator closest to curly L bar and curly L. Right. So that's the structure of my SO1, 4 algebra. Right. So now let's say I want to define what it means by going to the boundary. That is, when I take eta tends to 0. And the clever way one can do is that you define a coordinate which is eta tilde, which is related to eta as follows, epsilon eta tilde, and when you take epsilon tends to 0, keeping eta tilde fixed, you are essentially taking eta tends to 0. Right? So that is how I am defining this near boundary limit and going towards the boundary. Now, once you do that, what you find is that the CKVs that I showed in the previous slide, in terms of this eta tilde, they simplify a bit. So this L, curly LM and curly L bar L have this leading order component, which does not depend on epsilon, and the sub-leading order component is proportional to epsilon squared. And but the curly PRS diverges as you take epsilon tends to 0. So this blows up in the limit. Now to rectify this divergence in curly PRS, I define this operator, which is like non-curly PRS, which is defined as curly PRS multiplied by epsilon. Once I do that, what I'm able to do is I'm able to get rid of this epsilon factor, and then I can take the epsilon limit easily. Right, and the subleading factors will just go away, and you will have only these leading factors, and this then becomes your Poincaré algebra. And how do I know that this becomes the Poincaré algebra? There are a couple of reasons. First of all, look at this LM and LM bar, which are defined. So I change the vector fields when I take the epsilon tends to 0 limit of curly LM and curly L bar M. I replace it with LM and L bar M. So these again form SO1, 3 algebra, which is like SL2C. It is written in the form of SL2C algebra. And PRS again acts like the vector of these L and L bar. But now what happens is that earlier this commutator of curly PRS, that is non-zero and close to curly L and curly L bar, but now it becomes 0. So this is exactly your Poincaré algebra where this PRS acts as translations and they commute with each other, right? So what I can say in this through this slide. So first of all, firstly, what I meant is that in the near boundary limit, conformal group of Euclidean AdS 3, SO4, 1 contracts to ISO3, 1 with PRS as translation. That's one inference. Another inference is that the subgroup SO3, 1 remains unchanged. So earlier also it was the form of subgroup was the same, and after taking the limit, the subgroup SO3, 1 still remains the same. So it's still giving you SL2C, right? So it is undeformed. Only change comes with the commutator of this PRS, right? So these are the also SO3, 1 is an isometry of Euclidean AdS. So to begin with, we had SO4, 1, which is like the conformal group of Euclidean AdS 3, but SO3, 1 is an isometry of Euclidean AdS 3, which remains unchanged when you take the near boundary. So that's the key point of this calculation. Right. So now, what I want to see is that if you take the near boundary limit, your space is parameterized by coordinates eta tilde, z, and z bar. So you are still on some three-dimensional space line, but now your eta is replaced by eta tilde, z, and z bar. So how this group Lorentz group S3, 1, they act on these coordinates. So the way they act is that Z and Z bar, it becomes this SL2C transformation, the good old 2D conformal transformation law, and this eta tilde sort of get scaled by these SO3, 1. Right. There is the translations, they do not touch Z and Z bar, but they sort of shift eta tilde. So that's how in the new space time, which is parameterized by eta tilde, Z and Z bar, the Poincaré group acts like this. Also, because we started with Lorentz group, it was the isometry group of Euclidean AdS-3, and after taking a near boundary limit, what we get is this degenerate metric, which is given by d square and d. So why it is degenerate? You can see from here. Let's say if you take eta tends to epsilon eta tilde, you can the second term will be dominant when you take epsilon tends to 0, and then you can rescale that second term, and so you will get this degenerate metric, which is given by d square and eta. And again, this Lorentz group, you can see from this transformations that this Lorentz group, they act as the isometric group of this degenerate metric, d square and t. And the translations PRS, they act as wide or conformal transformations of this metric d square n. Right. So is this clear to now? I think you have any question. Please. Okay. So right. So before I move on to the proposal, what I want to summarize is that this conformal group of this Euclidean AdS-CFT in the near boundary limit becomes this conformal group of becomes the Poincaré group, becomes the conformal group of this degenerate metric. Right. So now let's go to the proposal. So first, the results of the previous slides can be generalized to any arbitrary dimension, like it's this one. Right. So in the near boundary limit, what now I can say is that this SOD plus 2, 1 contracts to ISOD plus 1, 1, and the subgroup, which is SOD plus 1, 1, which is like the symmetry group of Euclidean D plus 1 dimension Euclidean antidecimal space time, and also the symmetry group of D-dimensional CFT, it remains unchanged in this limit. So this is the okay. So this is what let's keep this in mind, right, before we go to the proposal. Now I just wanted to so this is like the diagrammatic representation, so one doesn't have to like look at the sentences. So I just want to focus your attention here. So this block, it just says that, let's say if I have a quantum theory of conformal gravity, or let's say quantum theory of like associated with this Einstein's gravity on D plus 1 dimensional Euclidean antidecimal space. Now the symmetry group of these theories will be SOD plus 2, 1 or SOD plus 1, 1 symmetry, right? And now from AdS-CFT, what we know is that they should be this part, and they should be dual to some conformal field theory with the symmetry group SOD plus 2, 1 or SOD plus 1, 1 symmetry, right? So this part, the top part is this AdS-CFT, right here.
What is an AdS-CFT that we decide? Or why you have to
No, I'm considering conformals. Usually when you talk about AdS-CFT, right, you talk about Einstein's gravity, and then you say that the isometric group of Einstein's gravity, which is SO3, 1, let's take 3-dimensional gravity. Then the 2-dimensional CFT, which is dual, should also have the same same symmetry group. But nothing is stopping you to consider conformal gravity at the conformal gravity in the bulk Euclidean antidecimal 3, and what it will just do, it will enhance the symmetries of your dual boundary theory. So your dual boundary theory will then become will have symmetry group SO1, 4 instead of SO1, 3. So I'm just sort of using that correspondence here. So this is purely based on the symmetry. So if AdS-CFT is true, right? Yeah. So,
the, 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 both having fluctuates. We're going to say impose conformal gravity on both. AdS-CFT is talking about the both CFT down boundary. All you know is the asymptotics down.
Yeah, so
Any of the conformal symmetries of the both, like if you let the metric fluctuate, they shouldn't be there.
right, so you're right. These are asymptotic symmetries. So when we're talking in the context of holography, we're always talking about the asymptotic symmetries of the gravitational theory, which are isomorphic to some global symmetry group of dual theory living in the boundaries. So when I'm talking about conformal gravity or infinite gravity with this sort of symmetry, what I'm implicit, and I should have mentioned that quickly, that these are asymptotic symmetries. Thank you for bringing that point, but these are asymptotic symmetries. Like, because again, like you said, it doesn't make sense to have like the bulk. All we have to do is the asymptotic symmetry. So these are asymptotic.
It makes, but these asymptotic symmetries will mix like the space-time symmetries of the CFT. That's why I'm confused. Like, these aren't like global asymptotic symmetries. They know it's a CFT. This is enhancing the symmetry group of the CFT.
Right. So
They
yeah. So they are
this conformal group, which is a space-time symmetry. In the boundary theory is now bigger space-time.
exactly. So yeah, thanks again. So the point is that you're right. The way it will work is that the space-time symmetries, once you enhance it, these extra symmetries sort of becomes like these internal symmetries of the CFT. So there is still a lot of research. I also work in this field where I try to understand how these extra symmetries can incorporate into these lower dimensional CFT theories. What I can tell you that they can appear as some sort of internal symmetries. So like I mentioned before, the Celestial CFT, the momentum operator, they act as the weight shifting operators, right? Which is an internal symmetry. So something like that should also happen.
Symmetry that doesn't create these concepts.
Sorry, what?
It's an internal symmetry that makes this possible.
No, but it sort of manifests in a weird way because let's say the symmetry will satisfy the symmetry algebra. Like by definition, it has to follow the symmetry algebra SOD plus 2, 1.
Right, but so the SOD D plus 2, 1 contains in it SOD the space-time symmetry.
Right. So it is yeah, it's a subgroup.
It's a subgroup.
Yeah.
So the symmetries do. This is an internal. You can think that
Also, when I say internal, I don't mean like some sort of these quantum numbers, like quantum number changing or things like that. When I say internal, I basically mean that we have like there might be some extra fields instead of so other than metric. You can have like metric on the like the boundary theory. You can have like say extra field. You can have like say anti-symmetric fields or symmetric sort of fields. So that will come into the picture, and then you can your gauge group will become bigger, right? So you can always have a CFT with a gauge group as 3, 1, but you can always expand that CFT by putting gauge group as 3, 2, and you just have to add extra fields. So,
when you do that, the gauge group and space-time symmetries don't have. Here,
no, they do act like they because because now these because of the additional matter fields that happen, your so your metric will also transform due to these extra symmetries. It does transform. I mean, yeah, it's a transform in a weird way, but it does transform. Like, there are works where, let's say, if you consider this two-dimensional theory with SO3, 2 gauge group, you can show that like there are these extra fields that transform under this space-time symmetry SO3, 2, but they do it in a weird way. So they do transform. Yeah. I mean, in my yeah, maybe we can talk about we can discuss this. But yes, I'm just saying that you can always enhance the conformal symmetry group. It will just mean that you are adding extra fields, like your background instead of metric will have, let's say, some sort of other fields. And but yeah, this can be done. Right? This is possible. Right. So
somewhat related question. clear that you can define a self-consistent CFT that has that mapped symmetry group?
Okay.
Is it clear that you can define a self-consistent CFT that has that symmetry group?
You mean this SOT plus 2 comma 1?
Yeah.
Yeah, it is. I mean, I'm working on some of them. Maybe I'll try to. Okay.
Sorry, that was not a question. These are, the conformal gravity theory, how do you get the SOs? Where's the scale come from?
There was this paper by the same, I think they get these AdS gravity from conformal gravity. You set the most secret.
The compensated engagement.
Yeah, you can set some of the views to 0 and then you can like recover the C. Yeah. Don't know technically, but the content was that then you can set some of the fields to 0 and then you will be able to recover answer.
This is not usually.
Right.
Yeah, it's weird because there is no scale.
Yeah. Yeah, I'm not sure about the technical. This would be right. So, okay. So now that the top part we have discussed, let's look at the near boundary limit of this part. And from the previous analysis, this previous slides, what we can say is that this conformal gravity and Einstein's gravity in the near boundary limit, they become some gravitational theories on degenerate manifold with symmetry ISO d plus 1 comma 1 and SO d plus 1 comma 1. So because this SO d plus 1 comma 1 remains unchanged, so this just goes as it is, but this SO d plus 2 comma 1 in this near boundary limit becomes this ISO d plus 1 comma 1. So in the near boundary limit, and also we saw that the manifold becomes the degenerate manifold. So your resultant gravitational theories in this near boundary limit sort of are theories defined on this degenerate manifold. Now, if we assume that this duality survives the scaling limit, what I can do is then I can come to the left hand side of this, and basically I can say that now the dual to these theories will be some field theories with Poincaré ISO d plus 1 comma 1 and as well as SO d plus 1 comma 1 symmetry. And we know that Celestial CFTs are the only CFTs that which have these Poincaré ISO d plus 1 comma 1. And similarly, you can have Celestial CFT with only SO d plus 1 comma 1 symmetry. So this is like the new sort of duality that one can propose based on this. However, you will note that I have put this question mark here because we don't know, because the way we got here was from the bulk side, because we thought that if bulk side is like this, so then the boundary side should be this. But we don't know a clear limit that will take us from this conventional CFT to the Celestial CFT with ISO d plus 1 comma 1 or SO d plus 1 comma 1 symmetry group. And it's like any if one can do that, then it would be like really nice. But so far we have not been able to successfully say what is this limit that they do that.
So are you then saying that it almost sounds like you're saying that the Celestial CFT would be dual conformal gravity instead of Einstein gravity?
No, so some gravity theory on degenerate manifold.
This less means O.
Yeah.
So what I meant is that the Celestial CFT will be dual to some sort of gravitational.
Oh, okay. And you have a Celestial CFT with SO d plus 1 comma 1.
Yeah. So this slash, right? So again, it follows from that. If you have a CFT with only SO d plus 1 comma 1, and we know in the near boundary limit, this SO d plus 1 comma 1 does not deform. So then the resultant symmetry group after the near boundary limit will also have SO d plus 1 comma 1, and this is what I'm going to discuss in this talk, right? So, and regarding your earlier question, what I meant, what this is essentially saying, that the Celestial CFT might be dual to some gravitational theories on this degenerate manifold. right? Instead of this not the AdS part, but when you get the near boundary limit. So that's essentially the proposal in nutshell.
Very low energy, the CFT.
Exactly. So there.
But it isn't just a contraction of the symmetry algebra. That's what you were doing. No?
Yeah, but how?
Thickness of the generators, and you know how to map the generators top boxes, and you do the same with left. It's not just that.
No, but because going from here to here, there's a fundamental difference that is happening. Like I mentioned before, here the Celestial CFT with Poincaré invariance will have distributional, should have a distributional nature of the correlation function. Like there should be some contact term. But to begin with, if you start with some CFT theory which has, let's say, power law, and you want to, let's say, define this sort of limit, we don't know there is any way to get a power law from a power law here to distributional.
Can't you study representations? I mean, you have all your generators, they are on some highest weight state, and you know how the algebra contracts. So what the generators are mapped to in terms of the epsilon.
Yeah.
Taken before, and you have the spectrum before and the spectrum after.
Generators, you can, I think you can, yeah, generators you can map, but I mean the whole behavior of the CFT changes, right? In this, there's some mysterious limit from here to here, where you where this behavior changes, but I don't know. You're right. I mean, I can send the representation, but I'm still not able to understand how the these 2-point function or 3-point functions which exhibit these power law behavior.
Fine, but you can study all the characters, the partition functions, the list of states.
That's true.
And this is way more than usually is said about Celestial CFT. So
no, you're right. That's why.
I don't understand why it's so mysterious. If it's well understood and just a contraction of global generators in the bulk.
That's true. I mean,
yeah, principally should be able to compute the characters of the left corner.
But isn't there a
Bottom left corner. And check that it's modular invariant.
But there are these lot of these problems that come about when you are doing this Celestial conformal field theory with this Poincaré invariance. Is like you need to have these this unitary representation of this SL2C irreducible unitary representation, right? So you need to continuous series representation of this SL2C, which people usually construct of this Celestial conformal field theory, right? But to start with, these CFTs are well defined, right? Even their let's say these are unitary CFTs, they are well defined, and a lot of the CFTs, the Celestial conformal field theories, they have these weird properties. I think what you're saying.
What I don't understand is that this diagram should provide the definition of the Celestial CFT. So you can complain about what is not known about the Celestial CFT. If I understand this diagram well, the top left corner you assume is known, and the limit, you know how it acts on generators, so you can define what is the left bottom corner.
So in this work, what we are very sure about this part, and that allows us to give you something here. But we did not look at how to go from here to here. But as you might be right, I mean, it's what, anyway, it's worth looking at.
I think so happens to be a boundary. Because you're ending up with determinant. Why would you? Is it obvious that it should be conventional?
Okay. Right. So that's the assumption in this whole part. Like if this AdS, if this duality survives its near boundary limit, then it should have some sort of a two-dimensional dual at the boundary, and we don't see any way why this should not survive this limit, right? So it just follows this duality follows directly from AdS-CFT dual.
I think I don't sound
Exactly. So that's what is the question mark. Randy, you're right. I mean, this is something, yeah, it's something that needs to be looked at. Even I don't have a proper idea like how do these things look, in this near boundary. That's why
The other contraction that's an alternate event on mechanics. We put some kind of spinning particle.
Right.
There's some very clear. If you always be very picture.
Right.
Exactly. Here you basically just go close to the boundary.
Right.
But what does it mean if you're grabbing here? Go close to the boundary.
You're considering some sort of small band near the boundary where your operators,
That's it. You grab. I mean, I can imagine you should feel for you. That's the question. But for if you always be very
okay, this field, combination to get the Einstein's gravity, limit, so this might be, let's, right, is there any more questions on this part? Yes.
Somewhat related. In the formal gravity case, I could sort of imagine how you might find something. Your boundary limit, Einstein gravity case, some. But in the conformal gravity limit, there's no scale. I think it's just the same confusion I had before. The scale, I don't know what it is. Or
Right. Right, there this radius doesn't act, it's just some sort of a parameter, right? Because it should exist if there is Einstein's gravity is the solution of conformal gravity. So yeah, then one has to probably look at that. But okay, there is a way when I will be discussing Einstein's gravity, I will sort of try to comment on this, like what can be the cost. Because I know for sure I have solutions of conformal gravity in Euclidean space-time, which like where you can get the Einstein's gravity solution by setting some of the fields to 0, and basically when you go towards the boundary of that theory, this conformal gravitational theories, you see that the vector fields, they like you can it's sort of intuitive to see, okay, there might be there's no problem at least at going to the boundary, but yes, physical issues of defining a scale, that that's something that one needs to. Yeah. How it's going to the boundary? Right, but here, actually, here when you go into the boundary, your manifold is actually becoming, degenerate manifold. But that's how the limit is being taken. That your there your analysis is near the boundary, but you are never actually taking that particular limit. There, this limit, the way we take it, it just becomes degenerate manifold near the boundary. So the resultant manifold becomes degenerate manifold. So this is sort of, you are sort of limiting yourself to near the band, some small dip near the boundary of Euclidean AdS, and you are working within that strip. So and then you can sort of
No, because I mean that's the whole point of holography. The two-dimensional CFT is capturing the whole three-dimensional bulk, not just a round. So also the physics inside AdS3 is captured by the boundaries of the two.
I see. Okay.
Not all some observables are only localized on the boundary and they are easy to manage, but there is physics also in the back. That's why holography is not trivial.
Okay, so this argument, I showed it for Euclidean AdS3, Euclidean D+1, but it can also extend to Lorentzian D+1 AdS. What I will just do is that your resultant celestial D-dimensional celestial CFT will have a symmetry group ISOT, 2 or SOT, 2. That's just general obvious representation. Now, one thing that I would like to mention is this scaling limit does not change the bulk isometry algebra, that's what I've been harping about, but it acts non-trivially on the coordination functions of bulk fields, which you will see it in a minute. Now, Therefore, in this limit, the bulk theory changes, right? And the word of question is that this identification that I'm doing is based only on the symmetries. I haven't looked at the spectrums of the operators or anything. I just look at the symmetries. So this correlation functions of Celestial CFT, we obtain this way, may not necessarily compute scattering amplitudes in asymptotically flat D plus 2 dimensional space time. This is the independent way of getting Celestial CFT correlation function. This may or may not be related to some flat space time. That's one has to see.
If this is just based on symmetry, then why we call it celestial? It's just a theory.
Right. So okay. So that's a very good question. Thank you. So the thing is that when if you're giving me two CFT, then for sure there is no way for me to tell now which one is Celestial CFT or which one is conventional CFT. Both have SO1, 3. But here we are looking at holographic CFTs, right? So when I'm looking at holographic CFTs, what it means is that if I'm looking at CFT with SOD plus 1, 1 symmetry here, or if I'm looking at the CFT with SOD plus 1, 1 here, the dual bulk theory is different. So therefore, by this logic, these two CFTs have to be different. So I have this answer only for holographic CFTs, but there is no clear answer to just if given two isolated CFTs that I don't have that reason for that.
No, but maybe the question is that you could obtain something that is not even inside your square, it's outside. Why the CFT that you obtain has anything to do with the Celestial CFT? Could obtain a CFT that has these symmetries and
yeah, but by definition, the representation theory, people study by definition, the CFTs with ISO D plus 1, 1 is called the Celestial CFT.
Okay,
good. Other, right? So that's right. Okay. So in this, so after we're talking about all these contractions of the group, what I want to show is that let's say if you have a 2-point function of a CFT on Euclidean AdS3, and if I take the near boundary limit, what happens to that 2-point function? And as you will see, it will just change the wave. So this is the expression for the 2-point function on Euclidean AdS t plus 1. As you can see that this is conformally related to some flat space 2-point function. If you ignore this conformal factor, this is just some flat space like 2-point function, and because Euclidean entity theta 1 is conformally related to flat space, what you can do is you add these conformal factors, which is eta 1 delta, eta 2 delta. So we will work with these 2-point functions, and x here is the spatial direction that I'm calling, which is like which lives in RD. Right. So in the near boundary limit, what happens is that this eta goes to epsilon eta tilde, and this becomes of this form. Now there are two different cases that I can do. Where I can expand epsilon in such a way, I get two branches of the correlation function. So one is this branch which is multiplied by epsilon t, another is this branch which is multiplied by epsilon 2 delta. Now, based on the dimension of delta, one or the other will have dominant contribution. So if delta is greater than d by 2, this will have the dominant contribution, and if I call it electric sector. And if delta lies between d minus 1 by 2 and d by 2, that will have the dominant contribution, and that I call the magnetic sector. Right. So first, let's look at the electric sector. So now, because there is an epsilon d, and this is the scaling, this is the field. What I can do is I can define a new field, which is phi tilde delta, which exists on these degenerate manifolds, this eta tilde and x, as follows. This will be my scaling limit. And now, in terms of this phi delta, what you can do is that you can, if you find the 2-point functions, so this 2-point function has this property that there is a contact term in the spatial directions, and this eta tilde has this power law type behavior, right? So now this is precisely what is known as this two-point function of Carolean conformal field theories, with phi tilde being the Carolean conformal primaries, right? And this is the two-point function of the electric sector of Carolean conformal field theories. Now, these field theories, they live on degenerate metric, which I have mentioned before. So this will be the metric here, right? So if you are not aware with the Carolean CFTs, so Carolean CFTs are those CFTs which live on Carolean manifolds. Basically, Carolean manifolds are degenerate manifold like this, and they have some additional structure. But the why this is relevant is that the null infinity, which is the boundary of asymptotically flat space-time, is a Carolean manifold. So therefore, another way of doing flat space holography is that you take the conformal field theory, which is defined on these Carolean manifolds. So that's where it comes to the picture. But let's not take that intuition, because I'm not at all like talking about that intuition. All you need to know is that this Carolean conformal field theories are defined on this degenerate manifold, which looks like this, right? And this sort of identification is not surprising, since Poincaré group is isomorphic to the conformal Carroll group in D+1 dimension. So this is an aside. You don't have to pay attention about this. But yeah, so basically in the electric sector, you get some Carolean CFTD, which is living on this degenerate matrix. That's the point. Now, as you can see that when d goes to when delta is d by 2, the numerator blows up because of this gamma function. But what one can do is one can extract this logarithmic term from this power law dependence of theta tilde, and the finite part of this correlation function as delta goes to d by 2 becomes this. So now in the non-conventional CFT, you know that this log branch comes from the scalar field who has 0 dimension, and if you want to look at the two-point function, there is log branch. There is something similar to that, but there is a contact term in for the spatial part, and this log term for the theta tilde part, right? So this delta equals to d by 2, because this form is contains log, it's not a conformal primary. However, if I take the derivative of the left-hand side with respect to theta tilde 1, what we'll do is it will just pull down this log, and you will again get the power law. So what I can say is that this derivative of the scalar field is a Carolean conformal primary, just like in conventional CFT, when you take the derivative of those spin zero field, it becomes the primary. Same cases here. But this is telling me an important thing. What it tells me is the unitarity bound. So it just says that in a unitary Carolean conformal field theory, the dimension delta of a scalar primary in the electric sector is bounded from below by a delta greater than d by 2, right? But if you now look at the conventional CFT d+1, this bound is less stringent. It is like d minus 1 by 2. So that's the and if you are wondering why suddenly I'm starting talking about Carolean CFT, please remember that when I was showing you the diagram in the near boundary limit, this Einstein's gravity or conformal gravity, they become some sort of these theories on degenerate manifolds, and those theories are called Carolean theories. So I'm just sort of talking about the properties of them. Right. So let's say okay. So I will just move forward. Won't spend too much time on this, but if I want to calculate the how this pi delta tilde, not this pi delta tilde transform under Poincaré group, I can just use the near boundary limit of some transformation of conformal primary and then x1, 4, and that will give me this derivation. And basically, that's the derivation I do in these slides. I can just define this Qi as this conformal symmetry operator, and the variation of delta phi will be just combination relation of this Qi with phi. And these vector fields, these guys can be like linear combinations of this curly LN and curly L bar N, which I defined previously. What you can see is right. So this is I would like to attempt to answer your question that you asked me in the first slide that was come to me. So usually when you are doing this SO4, 1, what you can see is that this curly LM and curly L bar M, their transformation looks like this, right? But PRS, the transformation looks like this delta phi delta minus delta phi delta. So then you're trying to calculate the representation theory. So phi delta, like the dilatation operator sort of resides in this curly PRS, right? Because that will give me the term proportional to delta phi delta. Then this is just SO4 comma 1. So now if I do this near boundary limit of this transformation and which is basically defined like this, and I define this phi tilde delta, I get this transformation. Now here you will see that the way PRS is defined, it just acts as some differential operator on del eta tilde, but now this LM and LM bar has this delta and delta, right? So the sort of this behavior change. Earlier, the representation were in the dilatation operator or the operators PRS were used to construct the representations like they were the they were the operators that these phis were eigenvalues. But now this LM and L bar M has this information of the conformal dimension. So in that sense, I was trying to say that the behavior of what are the representations and primaries will change under this Celestial CFT. Not the same as conventional CFT. So,
So usually the way someone gets Carolean limits described as kind of this hyper-relativistic limit. C goes to 0
Yeah.
and expand around that. Okay, but would that be a way of understanding what is meant by the near boundary limit of AdS?
Yes, it's in a crash
Yeah,
in the
yeah,
same way.
yeah.
you're right. Yeah, so I think that is also a contraction, and this is also a contraction, but the nature of the contraction, there might be some connection.
I was thinking geometrically, that's how you can get to the, if you're on a null trajectory, you can get to the boundary of AdS and find that parameter. That's in sense that to a null trajectory, according to a null trajectory, the boundary is close by. I was wondering if there might be more than just a superficial similarity between.
Oh, yeah, I think it might have some deeper connection, but let me think about that. Right. Okay, so these are the finite transformation of phi tilde delta under this ISO 3,1. And as I mentioned before, these fields they live on this digit. Right. Now let's look at the magnetic sector, the other sector, which will contribute when the delta is less than d by 2. For this, I just want to draw your attention that initially earlier for the electric sector, we have d by 2 here, but now this is delta. So the scaling changes, and once the scaling changes, what you can have is you can have a different 2-point functions where this is a good old power law, but it's just a power law in the spatial dimensions. So this is like, let's say if this is 3-dimensional CFT, this power law is just in the 2-dimensional dependence. So it's like a very trivial time dependence here. Now, also one can see that this lower bound is sort of the unitarity bound of the relativistic CFT, and the bound is between, it is both bounded from below and above by this expression, like it's greater than d minus 1 by 2, but less than d by 2. So what I can infer from whatever, like, so you can forget everything what I just said. Only thing to remember from this slide is that in the near boundary limit, if you have a conformal primary of, let's say, on the Euclidean entity sector d plus 1, it becomes an electric Carolean primary if delta is greater than d by 2, and magnetic Carolean primary if delta lies between d minus 1 by 2 or d by 2. So that's the only point to okay, so now from here, I'll just look at all the, these field theories on Euclidean entity sector 3, and I'll try to see, okay, what sort of behavior it implies. Right, so let's consider, okay, before we consider, I just want to write my Euclidean entity sector 3 in a different way. So Now, earlier it was in the Poincaré patch. Now I'm introducing this coordinate phi, which is related to eta s log eta. So I write it as follows. Gamma and gamma bar is just identically identified with z and z bar, right? So in this coordinate, the boundary is phi is that phi equals to infinity instead of eta will equal to 0, right? So with these coordinates, if I want to write the Klein Gaussian massive scalar field, it's given as follows, and the near boundary limit just now changes to this. The phi, it becomes minus log epsilon plus phi tilde, where phi tilde is these coordinate on this degenerate manifold, and when you take epsilon tends to 0, with phi tilde fixed, what you get is the action. So as you can see in this limit, the spatial derivative terms drop out, and what you get is just the term is proportional to like del phi tilde and squared phi square. So what you can see, what you can note here is that this action is invariant under SO3, 1. This SO3, 1 act as this scalar on the scalar phi tilde as follows, and this gamma and gamma bar is just these SL2C transformations, and this phi tilde prime transformed as follows. Now, as I mentioned before, that these coordinate transformations, they are also the isometry of this degenerate metric that I get after this near boundary limit, and in this coordinates that the boundary is written as follows. So there is this conformal factor exponential to phi tilde d gamma bar.
Why is the mass? It's the massive scalar cannot actually reach the map finite time. So should the data value prediction say it cannot?
No, but it's the way they just it doesn't get killed because we're going towards we're not going towards the boundary of that. Yeah, more progress towards this degenerate man.
Would you be scaling the rate of?
Yes, and yeah,
Right.
yeah, but this but like it still exists. Like it doesn't drop. It does not. Yeah.
So you think it's just a potential error lying on boundary time?
Not really, but as you will see, there's a nice like reason like there's a good like boundary operators if you want to define, they will depend on this mass rather than any equal. Right. So now this SO3, 1 symmetry, what I can do is I can enhance it to some sort of infinite dimensional symmetry. Nobody is stopping me, and my action will continue to be the will be symmetric under this infinite symmetries. And this infinite symmetry is just this gamma prime goes to gamma prime, which is function of gamma, and gamma bar prime goes to function of gamma bar. So these are like holomorphic and empty holomorphic parameterization. These are these Virasoro symmetries, and this phi tilde it just transforms as follows. So the usual field theory is not invariant, but this in the near boundary limit, this field theory that I get is invariant under this symmetries. Now, let's try to find the boundary correlation functions from this action. So to do that, I want to compute the first bulk green function and then go towards the boundary, right? So the bulk green function is basically the solution to this equation of motion that I get from this SMB, right? And so this it should satisfy this equation, and when you solve this equation, you find this particular solution. This is the green function. So you can see that there's a theta function in this phi tilde direction, and this delta 2 there's a contact term in the spatial direction, right? And then these are bunch of these conformal factors which are also there in when you are doing this scalar field theory in Euclidean AdS space time, right? And this delta plus minus is related to n square as follows, right? So if I want to transfer this expression back to eta tilde in our old coordinate, this will look something like this. So this eta tilde delta plus and eta tilde prime delta minus. So these are the conformal factor in front of this expression. Now I want to define some holographic this extrapolate dictionary that people usually define. So I can write this these scalar fields as some sort of this scaling in this eta tilde, this thing eta tilde, and some boundary operators. And when I substitute that in this Green's function, what I can see is that from there I can define these boundary correlators. So this is the boundary correlators corresponding to phi tilde delta plus, and O delta minus 1 is operator corresponding to phi tilde delta minus, right? What we see is that the boundary operator, the boundary correlators have this contact term, this delta 2 gamma minus gamma prime, and this is like the Celestial CFT type behavior where you have these correlation functions, and this delta plus delta minus is constrained by this equation, delta plus equals to 2, right? So this boundary 2-point function is a pure contact term because the theory is ultra local in the boundary direction, so it is fixed. These points are fixed and cannot move. So therefore, this is ultra. Therefore, there is a contact term, right? So the summary of this whole section was that in the near boundary limit in AdS3 plus 1, a scalar field of mass m corresponds to two boundary operators of dimension delta plus minus, which have this correlation function. So that is the
this kind of cultural count shows up on scale scribe.
right, exactly. Yeah.
But what I'm surprised that it's showing up your statement is spatial.
But here, okay, so thing is, I'm not, so first, after I declare the boundary limit, I have the degenerate manifold, then bar. Then I'm going towards the part where theta is going to 0. So somehow, I'm not going to spatial infinity, I'm going to, I'm just going to sphere which can be localized at the end of this degenerate manifold. So it's not the same as going to the spatial. Because I've already taken
that sort of like the boundary of that scribe minus.
yes, something is going towards the boundary of scribe.
That's first I should just want to correct. So, yeah, what I meant to say earlier related is that an null trajectory can bounce to the boundary back, in finite proper time interval. That seems to be related maybe with your boundary limit. But are you working in just the Poincaré patch or a maximum extended P?
Oh, so that's working in Poincaré.
Okay, then maybe this near boundary limit kind of going to the edge of the corners.
Yes, the corners of the
that intersect the boundary.
So what I can say is that this idea of that was proposed by Euclidean and before, where they do this slicing of Minkowski space that with the Euclidean antiphysical leaves, right? So what this is probably doing that, like in the near boundary limit, what you get is this picture that this Euclidean antiphysical is like sort of if they are if they're embedded in Minkowski space time. But I don't want to connect it with that because I'm looking at it as an independent thing, but I'm sure there is a connection there which one can like make it more articulate. But for now, this is like an independent thing. Right. Okay. So now this near boundary limit of string theory. Okay. So okay. Right. So we know that conventional string theories do not have target space conformal invariance, because the low energy effective theory relies on stability. So they are always this SO1, SOD plus 1, 1 invariant, like Lorentz invariant. Right. So according to our proposal, in the near boundary limit, string theories on AdS should be toward to Celestial CFTs with only conformal Lorentz invariants and not Poincaré invariants. So unless you give me some string theory which has conformal invariance in target space time, we'll just be like content with this because this is all what we can get. So right, so So this should be towards some celestial CFTs with Lorentz invariance. Right. So for this, let's consider a bosonic string theory on three-dimensional Euclidean AdS times some n, which is n is like for some compact manifold, which is some 23-dimensional compact manifold, and we do this in presence of NS field, NSB field, right? So now the way we take the background is as follows: ds square is L square d phi square. This I showed before. So the Worldsheet Lagrangian is given by this expression where G are the target space metric, B mu are the NSB field, and by and y mu are the coordinates of the target space, which acts like a fields on Worldsheet. So this is like the Worldsheet Lagrangian, two-dimensional Worldsheet Lagrangian. Now for the form of B, which you can calculate from the equation of motions, L square exponential phi, d gamma with d gamma bar, the Worldsheet Lagrangian on the AdS3 has this form. So you have del bar phi plus exponential 2 phi del bar gamma plus del gamma bar, and there's another action which corresponds to internal dimensions action. So the bosonic part of the Lagrangian, as one can see, is given by this West-Domino-Witten model for the coset SL2C, modeled out by this quotient SU2. So if you have this yellow book and you have this WCW model given that yellow book, and you take a particular form of G, their metric, and then you put into that action, you will be able to get this particular action. That's why this is written as West-Domino-Witten model for this group. And S int is the action which describes the string propagation on this 23-dimensional compact manifold. Okay, so let's now want to take the near boundary limit of this action. But to do that, first I need to introduce these auxiliary fields, which are beta gamma and beta bar gamma bar. So they are conformal, this holomorphic fields, they have weight 1, 0, 0, 0, and b bar gamma bar have weight 0, 1 and 0, 0. Right. So what you can so technically when you solve for the equation of motion of beta and beta bar, you should be able to get back the same action. But because of the when you are quantizing the theory, and when you're doing the path integral, the measure picks up certain direction. Because of that, that dilaton field is derivative. And similarly, that exponent can also be normalized. So you get this action, but you can always go back to this particular action. But for a flat space limit, sorry, not flat, for a near boundary limit, we work with this action because that's the action clearly give you something. Right. And also this alpha plus is related to string length and AdS as follows. Length of AdS this. Also, K is will come back to what is K. Right. So now one can clearly see that if I take phi tends to infinity, the last term drops away, and you get this free action. And this free action is given by this, right? And now the equation of motions for beta and beta bar is nothing but just del bar gamma equals to 0 and del gamma bar equals to 0, which says that your gamma bar and gamma are this holomorphic and anti-holomorphic map from the Worldsheet to the boundary sphere. So what is happening is that when you your Worldsheet is sort of wrapping your target space boundary, right? So the target space boundary, if it's S2, then it's wraps that, and therefore this Worldsheet instant on, if it has a non-trivial cycle, your target space or wrap strings are known as long strings. Why call it long strings? Because you are taking the limit where you are going towards the boundary of this AdS3, right? So that's why it's called the long string. So the strings is stretched and go towards the boundary of that. So okay, because this action is can be written in terms of this West-Domino-Witten model. It has one can show that it has an affine SL2 times SL2 symmetry at level K, which is generated by these Worldsheet currents J and J bar. A takes value from 1 to 3, which is like the group dimension of SL2R. And these affine symmetries will generate stress tensor, Shubhavara stress tensor with central charge C, which is given by 3K divided by K minus 2. So this is all well known. So not it will not. I just stating the right. So in the paper by Gideon and Cyberg, what they showed was that the symmetries of this worldsheet action can be lifted to space-time, and it becomes the Belastovo algebra of the dual CFT2. And this central charge of this dual CFT, which describes the long strings, is given by C space-time equals to 6kp, where p is the number of times the worldsheet wraps the boundary, right? We will only look at p equals to 1, where the worldsheet wraps the boundary one time. So we'll just work with p equals to 1. Now, in another one, which was done by Cyberg and Fittel, they argue that the space-time CFT2, which describes the long strings, it contains the Liouville field phi tilde with the improvement term Q and central charge CL. And another things are the modes on this S end, right? And the modes of the fields on this compact manifold, 23-dimensional compact manifold, that describes the location of the string. And these modes have this central charge C8, right? And what they showed was, because essentially the central charge from both of the calculations should be similar, so should be equal. Basically, you get from the work of GKS that the space-time central charge is 6K, and then and Cyberg showed that the same configuration can be explained by let's say Liouville field theory and this internal modes, right? And you have to equate the two. CL plus C equals to 6K. Now, the Liouville field theory has an expression in terms of this background charge, which is given by 1 plus 3Q square, and C int is given by 26 minus 3K divided by K minus 2. So the way this is calculated is that in the absence of ghost, what you get, not in the absence of ghost, sorry. The matter field should have the total central charge equals to 26, so that the ghosts can cancel it if they have minus 26. So from there, we get C8 as follows. And now you put the two of them together, and then you get this Q equals to K minus 3 and K minus 2. This is like the equal. Now, what it says is that this Liouville field, it describes the radial phi fluctuations of the long string worldsheet. And this space-time CFT2 dual to string theory, which is described by the worldsheet action SLV, is an example of Celestial CFT with OP Lorentz invariance because of the proposal that we give. So that's basically this is what we are trying to say, that this the dual CFT that describes this long strings are like an example of Celestial CFT2 with this Lorentz. So that's the.
So why is it Celestial?
Okay, so because it's a holographic CFT, and so the only why it is celestial, what I'm saying is that because the bulk theory, which is described long strings, it's sort of going towards the boundary, so it's not the same bulk as the full AdS3, right? So the bulk theory changes, and because the bulk theory changes, the CFT behavior. There should be some change in the CFT.
What is the feature of this CFT that makes you call Celestial CFT?
Right. So I don't have a good answer to that except for this fact that this duality that we have, because these are holographic CFTs, if the bulk theory is different, then they cannot be the same CFT as you started with, which is like this.
Sure, but why should it be the one that is the protagonist of this celestial holography? You're just taking a limit of AdS3 CFT2, but why should that have anything to do
non-conformal group, it becomes Poincaré group, right? But both of them have this Lorentz invariance. So when you take the near boundary limit, even though the full conformal group becomes Poincaré group, the Lorentz algebra remains undeformed on both the sides, right? So this Lorentz invariance, this Lorentz algebra is a subalgebra of the Poincaré group. So it has to, it's fundamentally sometimes different from the Lorentz algebra, which was the subgroup of SO, let's say full conformal group. So it is in that context I'm saying that this is Celestial CFT. Just by argument, it's based on holographic CFTs because the bulk theory changes and bulk theory will have, let's say, Poincaré invariance. But if the bulk theory doesn't have Poincaré invariance, if the flat space limit, even though SO1, 3 does not change, the bulk theory changes because you are taking flat space limit, and that's why I'm trying to argue that this is Celestial CFT. Essentially, yes.
You're not taking the flat space on the.
No, I'm not taking flat space. I'm taking clear boundary.
Why you say flat space?
Oh, I'm sorry. I didn't read that. Yeah, so whenever I meant near boundary limit, not flat space. So if the near boundary limit, conformal group becomes Poincaré group. Both of them have SO1, 3. But now essentially the behavior of that SO1, 3 has changed courtesy of the bulk theory, because when you take the near boundary limit, the gravitational theories in Euclidean AdS becomes gravitational theory on the degenerate manifold. So that's my reasoning to differentiate both the CFTs. And that's just reasoning based on holographic. Nothing, not of the intrinsic property, because that I haven't studied.
Holography, these things look very different, right? Started by saying that flat space could be multi-specific. Here you're looking at both gravity, one dimension lower. That's on some degenerate manifold. Now you're saying gravity on some degenerate manifold, one dimension. Same as gravity on flat space, one dimension higher.
I have not claimed that. I would like to see if this is possible, but that's an independent calculation. But
without this, there is no celestial log.
so there must be some sort of a connection that I have to, that it must be connected somewhere, it must be connected somehow, but I don't have a proper answer as of now to give. Right? So I was attacking the problem independently from this AdS-CFT, and I think there might be some connection to it, but I don't have the answer. Okay. So the final part is just near boundary limit of, sorry.
Maybe you can try to wrap up.
Yeah, it's fine. So I'll just so the final part is this near boundary limit of Einstein gravity. Now, basically, the important thing to note is that when you write Einstein-Hilbert action in this particular gauge, there are two terms. First, this term, and second one is the Ricci scalar term, which is on this two-dimensional boundary. Now, in the in the near boundary limit, this term drops out, and you only get the first term. And the consequence of that is that when you are trying to look at the solutions of this theory, the solutions now you can write the solutions of this theory as follows. First, you start with this degenerate line element, where your only field is Hij, function of phi delta and xi. Now, the solution of this equation of motion coming from this action is this. So this will look to you more like the solution of locally Euclidean AdS-3, but there's one difference. The difference is because of the term that dropped down in the near boundary limit, the H1 the free data, which you can also call it like holographic stress tensor, it is traceless. Usually in the Euclidean AdS-3, it is proportional to some Ricci scalar, sort of saying that there is a conformal anomaly, which is absent from here because of that term that dropped down. And the conservation of the stress tensor, this H1KI, it just tells me that you can have two copies of, like you can have a holomorphic and anti-holomorphic component that will generate two copies of Virasoro algebra with zero peripheral term. So that's the So that's what happens when you look at the air boundary limit of Einstein's gravity. So this central charge term, it's cross. Right. So now I just conclude it. It's not right. So I would like to conclude with this particular diagram. It's not the same diagram. Just so basically we had the duality between some gravitational effective field theory or string theory on AdS3 with NS flux that was dual to some conventional CFT on the left hand side. But when you take the near boundary limit, this gravitational EFT, it becomes the 3D Carolean EFTs. And this AdS3 with NS plus, it becomes long strings. And they are dual to some Celestial CFT with the with Lorentz invariance. So in this talk, I focused on theories with only Lorentz invariance, but then these results can be extended to conformal field theories and conformal gravity on Euclidean anti-de Sitter 3, and you get like some really interesting results. From there, you can also get BMS algebra. That's what I'm trying. That's what I'm currently working on, and the existence of this Liouville sector in this long string CFT2 suggests that the Liouville sector could be like a universal feature of all the CFT2. As I mentioned in the introduction, that there have been recent works where people have calculated these Celestial CFT with only Lorentz invariance, which are just Liouville theory coupled to some matter fields. So that's the and last thing, our observation sort of resonates with the fact that in this high energy limit in asymptotically flat space-time, one can identify the string worldsheet with the Celestial CFT. So this was the work by Simon and Taylor. They said that in the high energy limit, when you analyze the scattering amplitudes, string scattering amplitudes, this worldsheet points on this worldsheet can be identified with the points on the Celestial speed. So people would probably like to see the connection between our work and but yeah, so that's right. Thanks. Yeah, I'm going to over time because
Maybe key questions for and let's thank you again. Man, shouldn't this all be derivable? Okay, what you call the CFT2? I mean, how do we stop that? Yeah,
Still don't believe this picture.